Evening to everybody. And this is the final session of this week's training course. It's a little bit sad and a little bit of a relief for all of you because it's been pretty intense, I can imagine. And but anyway, we will have a little feedback session later, but it's my pleasure this afternoon to introduce the session. And the way we structured this session was we've talked about hadron therapy technologies, where and what it can do. So this afternoon wanted to show two examples of accelerator technology coming into a real application in the real world. And then a presentation by Jeff Buxbaum to say hadron therapy and particle therapy is of course great. That's what we've been hearing about, but always one has to keep the bigger picture in mind as to what the challenges are facing us. So that's really the way we've sort of tailored the last session. So I start off by introducing you to Alberto De Giovanni. He was a PhD student when I first met him. And now he's the Deputy Technical Director and Group Leader for Accelerator Physics at AVO and ADAM. He will tell you much more about this. And he's been working there for 6 years in design, development, and testing, as well as overall integration of an accelerator complex with proton and ion therapy. After his master's physics at the University of Milan, he's been working in the field for more than 13 years. And of course, as you know, I told you that everybody around here goes through Ugo Amaldi and Terra, and he's no exception. So he did his PhD with Lausanne EPFL, including in collaboration with Terra and CERN, and a CERN fellowship working on high frequency RF Linac tests for compact accelerators. But now he's going to tell us about AVO and ADAM. Thank you, Alberto. Welcome. Floor is yours.
Thank you very much, Manjit, for the invitation. And I'm going to do this presentation on ADAM and light, as we discussed in the program. I feel a bit the responsibility to be in this last session, but I'm also happy because I think some of the concepts, some of the ideas I will talk about may be resonating with a lot of the things you have seen during this week. And so I'm happy that you had already a lot of presentation in the past few days. I've seen the program and I'm very happy that this can be now, I can bring in some ideas related to this. So here you can find my email address in case we want to stay in touch and to contact me after. And so let's start with the presentation. So ADAM and light, or light and ADAM, and these are a bit cryptic. So I decided to start with saying what are these two acronyms. So light stands for LINAC, for image guided hadron therapy. And you see here a few pictures of the accelerator itself. And this is the LINAC technology. And then ADAM instead stands for applications of detectors and accelerator to medicine. It's a Swiss company based in Geneva. And you see here the logo of ADAM and born as a CERN spin-off. So the two topics of this lecture will really be the light accelerator, that we call it sometimes also light product, in the sense that we are really developing this accelerator as an industrial medical device. And the second part of the talk will more deal about ADAM itself and the industrialization process. So ADAM, I said already, CERN spin-off company, has been bought by a UK company. It's called Advanced Oncotherapy, and in short is AVO. That's why AVO ADAM. And you will discover what this picture means along the presentation. So let's start with light and with the LINAC for image guided hadron therapy. So when talking about hadron therapy, well, we all have in mind this picture here, I think, and you probably have seen thousands of times by today. But I still like to show it because it summarizes all the effect, all the depth dose curves for different types of radiation sources used in radiotherapy in general. And you see, for instance, cobalt-16, you see X-rays, and neutrons, so all type of radiation used. And we see here in particular the Bragg peak that is typical for proton and other types of ions. And it matches the ideal case where you can deposit all the dose at a given depth inside the tumor. But what's important in this picture also for me is also that you can modulate the depth that you can reach by changing the input energy of the beam. And that is crucial, and in particular for a LINAC like the one we are building. So with such type of radiation profiles, you can generate conformal plans. And this is really the initial and overall clinical motivation for the use of proton in radiation therapy. Now, when we pass from clinical needs to the beam and the system, the accelerator requirements, we need to translate basically this idea and these needs into beam parameters and into what are the capability of your machines. And basically, when you see the Bragg peak curves, or let's say from the clinical point of view, we want to reach tumor that goes deep inside the body, and typical energies that allow to reach such a depth are in the order between 70 and 230 MeV for protons. And the typical current or the flux of proton you need is in the order of 1 nanoamp. And this translates into something like 6 billion protons per second as an average value. Then you go through scanning magnets. Since protons are charged, you can use scanning magnets to paint the tumor transversely. But most importantly, what we target with the LINAC machine is also the fact of being able to paint the tumor in a very fast way and in electronic way, also longitudinally. So basically, the requirement of the beam spots for the light system include a variable charge to be able to modulate the height of all these Bragg peak that eventually can generate the conformal dose. The variable energy achieved with fast and active electronic energy modulation without the need of absorber in the energy range between 70 and 230 MeV, and then variable spot position with a transverse painting of the beam. So all this is the so-called spot scanning technique. And these are basically the basic requirement for our light machine. Now, in terms of technology choice, we are looking to high frequency LINACs. And the initial proposal for high frequency LINAC dates back about 30 years ago. Already in 1991, there was a first paper describing a design of a all LINAC approach where you have a machine of about 28 meters that uses high frequency accelerating structures to bring the proton to such high energy. Shortly after came also the so-called CycLINAC proposal. You probably heard about it also in the opening lecture from Professor Amaldi. And here the idea is to replace the low energy part of the LINAC with a compact low energy cyclotron that can be used to inject the proton into a high frequency LINAC that is used to boost the energy and to bring it to the therapeutic range. So all this is very well described in a review paper that you can find here cited. And so what is light? Well, basically light builds up on these initial ideas to make a beam production system for proton therapy. And it's called LINAC for image guided hadron therapy because one of its features is really the fast energy variation. You see here a sketch of the light system, which basically shows the LINAC, which has a length of about 25 meters, include different sections, as you will see also later during this lecture, and allowed to reach maximum energy of 230 MeV, and has an output peak current that range between 0.3 to 40 microamps within very short pulses. Typical pulses for this machine, which is a specific feature characteristic of LINAC machine is the fact of being pulsed. So the pulse length, it's in the order of a couple of microseconds, but there are 200 pulses per second. So that's how we get to what I told you in the beginning, this 1 nanoamp average current, or 6 billion protons per second. So all these, it's achieved by using RF structure where the radio frequency field has a frequency of about 3 gigahertz, 2,997 megahertz. But so one question can be, why 3 gigahertz? What is so special with this number? Well, if you look at conventional radiation therapy, and there are more than 10,000 machines that are used daily in all the hospitals for radiation therapy, they would look something like this. And if you look inside, there are this type of copper tubes that are basically stuck of accelerating and coupling cells, about 1.5, 2 meter long, that are used to accelerate electrons up to an energy in the order of 4 up to 20 MeV, 25 really maximum, allowing basically the electron to be accelerating, hitting a target to generate photon X-rays radiation field. And all these machines, they all work at this 3 gigahertz frequency, which was the first frequency used to produce also the first research LINAC in Stanford University in the 50s. And since then, basically all the industry has developed a lot into producing all the different subsystems that are required to make this machine work. So the 3 gigahertz frequency is already industrial and fully developed standard for this type of application. So there are medical LINACs that used in conventional radiotherapy based on this frequency. There are RF power sources, all the RF network and transport components that are readily available. So the initial choice of this 3 gigahertz was pretty obvious. And on top of it, it allows to make a compact machine. The size of such an accelerator transversally, it's in the order of 20 centimeters. Well, but I say these are used to accelerate electrons, and we want to use it for protons. Can we just replace and just put protons into these tubes? Well, not really. We need to think about what happened in the acceleration of particles, and in particular, for those of you who have done a bit of relativity or physics during their studies, well, you know the rest mass of particle is pretty important. And here you have really a picture that shows what's the effect of accelerating protons, which has a rest mass of about 1 GeV, with respect to electrons, which have 0.5 MeV mass. Well, the electrons already, after few MeV of kinetic energy, they reach a speed that is basically the speed of light. It's basically beta equal 1. For protons, instead, when we look at the energy range we are interested in, 70 to 230 MeV, well, the speed of protons in this range, it's in the order of 37 to 60% of the speed of light. So there is a very important difference between these two particles. They are both charged, one negative, one positive, but their velocity profile is very different with respect to kinetic energy. And so we need to take this into account when designing the LINAC. And also we need to think that, okay, the energy gain of the particle for electron machine, it's in the order of 20 MeV. For proton, it goes to 230 MeV. So it's 10 times bigger. So the idea is that, okay, we can reuse the same concept, but we need to make it modular to generate multiple units, and each unit will be adapted to the increasing speed of the beam of particle. And that's basically how the initial design of the light machine started, thinking about RF units that are used to power cell-coupled Linux structures, the same type of structure used in radiotherapy, but adapted to the proton therapy acceleration. And here you see the, let's say, the sketch, the 3D model of one RF unit, which includes its RF power source with modulator and klystron system. It has a very compact size, and the RF power that is amplified by the klystron can be transported through this system of waveguides all the way to the RF modules. And the RF modules are made of this structure called tanks. And you see they are alternating. So there is space between each tanks, and this space will host quadrupole magnets. So let's start with the accelerating, so the RF part. It's basically something like this, where you can see cut through of the accelerating module. These are the tanks, and they are connected with this structure called the bridge coupler. And the power that comes from the RF module, from the RF power source, is injected and is split among the two tanks. And here is the space hosting the quadrupole, very compact, very small permanent magnet quadrupoles. And the basic acceleration process takes place really in this little accelerating cell. So each of these, it's one accelerating cell, and you put a stack together to get the full acceleration of the beam. So what's happening inside this cell is that you have RF field, electric field, that is changing sign with this 3 gigahertz frequency. And basically between one cell and the next one, you have a certain delay, and the design, and this I promise is the only 2 equations that are part of this presentation, but that just to give you a flavor of how the design evolved and how the design is made. It's basically based on this very simple condition that is this called synchronicity condition, where basically the time it takes for the particle to go from this accelerating cell to the next one is such that so the distance between 2 cells is sized in a way that the particle will take the correct time to reach the next cell, the same time it takes for the electromagnetic field to reverse sign. So basically the velocity and the length are linked together, and you see that the length of this structure depends on the speed of the proton and on the wavelength of the field. For a 3 gigahertz field, this lambda, it's 10 centimeters. So we are having here a stack of cell which distance is typically in the order of between 2 and 5 centimeters. So having said that, we can modulate the energy of the particles by really changing the amplitude of the electric field, or by playing with the phase of the electric field. And this is really the basis of all this idea of using Linux for proton, to have really the flexibility to allow the energy of the beam to be changed electronically, just by changing the electromagnetic field inside the structure. No needs of absorber or degrader or mechanical pieces that move into the beam line. So this is really one important aspect of this machine that it's important to pass, and so why it's so unique, and also why it's so challenging. And just as a little example, this is show you what happens inside in this idealized manner, where basically you have a particle. Let's follow this simple particle that goes through the different cells, and you see how the synchronicity is kept such that it runs from one cell to the next at the correct time. This example, the field was changing 5.7 gigahertz, but the concept is the same. And now I talk about the RF, but there is another key ingredient, which are these little magnets here, permanent magnetic quadrupoles, because you have seen probably also during this week in some of the lectures how the beam transport evolve along a transport line and along accelerating modules. And you see the beam tends to diverge. But if you put a quadrupolar field that has this type of magnetic field line, and you play a little bit around with Lorentz force, you try to remember this right-hand rule, you will see that basically a particle going towards the outer side of the PMQ is pushed back by the presence of the magnetic field. And so that is why we say the quadrupole are focusing the beam. And now, okay, if you do the same on the vertical plane, actually this same quadrupole will be defocusing the particle, but then it's where basically we place a sequence of focusing and defocusing quadrupoles such that we can keep the overall focus of the beam, and we can transport the beam through the different accelerating units. Okay, with this, you have all the basic ingredients for an accelerating unit. And this was done as the first test on a high frequency LINAC for proton therapy. It was mentioned probably also already during this course in the first lecture, was so-called the LIBO, the LINAC booster prototype, was built by Tera, CERN, and the NFN in the year 2000. And it was used to accelerate protons between 62 and 74 MeV. This was really a research project, a proof of concept. And this was very important to start all this design. Now, the same design was taken over by Adam, as one of the first big projects of Adam was to basically adapt this design to an industrial production of such a unit, which is a 3 GHz LINAC unit for proton therapy that has been produced and built following the industry standard in the year 2009-2010. This was tested already as a small unit prototype. Since then, Adam, and then after that was bought by ABO, well, we have developed the full LINAC design, not just one unit, but the full sequence of LINAC. And to do that, we need different type of structure. The key features of such a LINAC machine is, I already mentioned, a pulse beam at 200 Hz, the active energy modulation, no needs of mechanical degradation, possibility of having a beam that is pencil-like, perfect for the spot scanning technique, and the modularity of the system. So the system is modular and made of different parts, different sections. We start with a source, which we call it proton injector, which allow us to generate the first protons. We collaborate with external supplier, and within AVO Adam, we have adapted and optimized the source and the low energy part for variable intensity. And then we have the real RF frequency structures, where we have a radio frequency quadrupole, which was originally designed by CERN. One example, probably you have heard from Giovanni Anelli during the course of this week about the patenting and the way of CERN of working on this project. And this is one example of CERN development. And then collaboration with Adam, we used the first prototype to accelerate beam. And since then, we have got a license for the design, and we have built a second one fully based on industrial production. Then we are using a second section, which is the low energy section of the accelerator based on side-coupled drift tube LINAC, where the original concept come again from a research institute, which is INEA in Italy, and the Picardi collaboration. And this was tested with beam in INEA, but the same design has been applied to the light machine. And so the responsibility of AVO Adam is really industrialization of such a design for mass production. And then the CCL, it's coupled cavity LINAC, what I described before, based on this LIBO concept. And then again, designed for all the modules and for all these implementation, where you can notice that, for instance, this low energy part has shorter tanks than the high energy. And this is really due to this synchronicity condition I explained in the beginning. So the acceleration of the beam takes place along these modules. What we did in the 2017, 2018, and 2019 was to prepare a first LINAC feasibility project in Geneva based on CERN campus. This is on Saint-Genis-Pouilly, where we got a bunker of the size of, yeah, maybe 2 big garage, 16 times 4 meter, and we could install a prototype, a first version of this LINAC, which allowed us to demonstrate the acceleration through all these different type of cavities. And this was done in different commissioning steps at different energies, and maximum energy of 52 MeV was reached. And then, okay, there was no more space in the space we were assigned, so we couldn't build the full machine there. But the purpose of this was really a demonstrator to allow to make sure that from the technical point of view, the feasibility of running this different type of structure would work. So it's a very important stage, this demonstration and this technical feasibility stage. Here you have some pictures of the different cavities. So it's very crowded, a lot of cables and of services. When we talk about the LINAC, we think about this, but of course there is a lot of more other subsystem, a lot of more other elements, equipment to take care, vacuum, cooling, electrical controls. All this is integrated into this demonstrator. In this you have a view of how the machine would look like inside this small bunker. And what we could demonstrate was really, apart from the ramping up of the energy of the machine in different installation phase up to 52 MeV, was really during the 2019, two important aspects of this machine that are both features and challenges for this machine is the fact of the versatility. So the intensity modulation, the capability of changing the intensity, and the fast active energy modulation. You should notice in this scale, that was a test that we did in this demonstrator, the time distance between this stick and this stick, it's 1 second, and we could change the energy 100 times. So at choice, every 10 milliseconds here, we could change the energy of the beam and use it to paint, to write something in energy. And this measurement was also done with something we developed within Adam, that is a fast energy measurement system based on time of flight. So all this was really important step to move forward with the project of building a full machine based on this technology. And that's what we are doing now. It's a full-scale integration project up to the 230 MeV. And this is done at the STFC Daresbury laboratory in UK. And this is a technical test site. It will include not just the accelerator, but the full accelerator and medical treatment system with 1 treatment room. And there is a partnership with University Hospital of Birmingham to aim at treating first patients in Daresbury in the context of the certification plan. And that's an important point. Certification is part of the activity as well, that one should think about. It's not just the technical aspect, it's not just building the machine, but it's really the full process. And so I have this maybe short video to propose to you. Instead of going through picture, I thought it's maybe worth to share with you this video to show you how it looks like. Can you hear the sound of the video?
No, we don't hear it.
Okay, so maybe I just need to.
Our journey begins in the northwest of England.
Yes, now.
Laboratory of the UK's
Yes, it works.
Yep.
Okay.
Where we have set up our manufacturing site for the assembly and integration of our modules.
Perhaps you could turn it up a bit.
Yes.
To begin, we created an accelerator hall to house the gallery of accelerators, the light system. Walls and ceiling, top to house heavy driving units. The accelerator, currently under construction, 4 IoTs operating operating at 750 megahertz, 30 electrons operating at 3 gigahertz, all supplying RF power to the accelerators, and is cooled, kept under vacuum, and monitored by beam diagnostics and our time of flight energy measurement algorithm. DC supplies in the system drive magnets which control the position of the beam, and a full control system keeps the entire system working.
Alberto,
Yes.
I don't know if the video is moving.
Where our specialist operators accelerate and steer the proton beam.
Is it better now?
No, I think video seems to be stuck.
Proton source known for its stable operation and long lifetime, and with a supply voltage of 40,000.
Can you see the video now?
Yes, we can. Yes, thank you.
Volts. From there, the protons start their journey along a gallery of accelerators, moving as a 200 Hertz pulsed beam, through the CERN-developed RFQ, through 4 SCDTLs, and finally through 15 CCLs, accelerating up to a maximum of 230 MeV. The patient treatment itself, which is the final goal, takes place in the treatment room at the end of the accelerator. This has also been built at Daresbury, where we'll undertake our clinical investigation plan and first patient treatment in conjunction with University Hospital Birmingham. We've installed a state-of-the-art robot chair with CT scanner and X-ray panels for accurate patient positioning. Patient treatment workflow begins with patient scanning, controlled from an internal control room. Then a patient position cross-check with the robot chair ensures the patient is in the correct treatment position. And then treatment can begin. The light system offers the unique feature of electronic energy modulation, obviating the need for absorbers. This results in a considerable reduction in the thickness of the radiation shielding that's required. In addition, the light system has a very high proton beam transmission efficiency. Light contains over 34,000 separate components, integrates more than 300 separate devices, and accelerates protons up to 60% of the speed of light. There are over 250 front-end control software instances newly developed to accelerate, steer, and monitor the proton beam. It utilizes 20 gigabytes per day of data capture in beam optimization and control, and delivers a proton pulse at your energy of choice every 5 milliseconds. Light from Advanced Oncotherapy. Advanced Oncotherapy now.
Okay, that was for the video, just to give you an overview. And this closed the first section of this presentation about light. And now I think I can spend, I can spend the last few 10 minutes or so on the second part that relates more to Adam and to the industrialization process. I thought, okay, we talk about the technology, but let's talk a bit also of what is behind it. And so now you see a bit of explanation of this iceberg picture. Let's think about the technology, or the LINAC in this case, as one technology application that has interact with several other parts, which is, for instance, the users or the clients or the operators, but also it allows you to discover new opportunities or to use it in different environment to cope with, for instance, organ motion, to use the machine in different settings and for different application. But what's behind this, it's also something that maybe we don't see so often, but it's a whole set of activity and of work that is done on the production, commercialization, documentation, certification, the quality process development, the product development. And there are interaction with several aspects that you may have seen as well during this training, during the course of this week. For sure, there is at the start a lot of research and development, but there are, for instance, intellectual properties, patents, patenting. There is a lot of testing involved, verification and validation. There are discussions about supply chain. There is regulatory aspect. I think you also had the presentation on this topic, so I think it resonates also with what was said about Med-Ostron and so on. There are standards, and last but not least, also funding is an important topic. Well, this is really one way of seeing it. The other way that for me it's also maybe a simplified way, but it describes a bit what happened in the case of Adam, and what happens in quite often is that, okay, we have a product that comes to real world or to the market by industry, but the roots of it are quite often coming from research labs, from academia, so from basic research, and this is transferred then to the real world application. And so I want to take a bit this example to showcase what we have done. So Adam, as a medical device company, is following the industry standards, that is the ISO 13485, and this basically relies on quality management system and on processes for the development of the medical device. This means you need to set up the framework for this to be done, which include the process and production control, the design control of the different equipment you are building, the product surveillance once you have it online, the resources allocation, the management and the responsibility within the company, and all these change management and corrective and preventive action are also part of the quality management system. This is part of the work that has to be set up in order for the product to be developed. And the flow is really of such a product, for instance, the Linac, it goes really from the user needs. And we discussed at the beginning about clinical needs, what the user wants from this machine, from this Linac. Well, then it goes through the design and design input. And here the input can come from many different sources. There is internal development, there is literature search, there is maybe some other groups have developed something that can be used in the design. All this is part of this process flow. And then so the design research activities really are based on all these inputs. And what you come out is at the end with a design of a machine, of a product that should be verified with respect to what you had as input. So the verification process really make the loop here of what you have designed. Does it meet what you have requested the design to be? But then from that moment, you really can go into the production phase and the installation phase, where basically you can perform another type of test. This was verification. Now here is the validation test, where basically what you are asking is not does the machine do what I have designed it for, but does the machine do what the user wants? And this is another important step of this process. And then we go from there to the certification and possible commercialization. So all this has to be taken into account when we pass from a research project to an industrial development.
So Alberto, 5 minutes, please.
Last 3 slides.
Okay, thank you.
We are getting now from this design and development. So in this design and development roadmap, through these different steps that I mentioned already before, conceptual step, all the way to product development and verification and validation, as I just explained. And only then it's basically the possibility of having it on the market. And so this is also interesting to see it in the view of what can be called the innovation chain. So how the ideas from science are converted into real applications. And I think I found this picture very interesting. You find here the source. It describes it as a chain going from academic research through collaboration to industrial application. And this is a bit also, I want to picture it in this way, through different TRL, which are technology readiness levels, from a first phase of knowledge development, basic technology research and basic research ideas applied then through some feasibility proof. We have seen it for LIBO, for instance, and then some technological demonstration, a demonstrator like what we built in Geneva, to go then through this development to the first pilot plan, and then from this to scale up. And really, I think these are different aspects of this project that it's quite interesting to look at them through this chain. And so these technological readiness level are really steps from research to innovation, and all what basically you are doing also as training or also studying in fundamental research or in applied research is very, very important then as input to the next stages and to the possibility of developing systems that then can be used into the real world. So again, taking back the analogy with this apple tree, well, you start from an idea of the apple, but then you have some roots that are really down into basic research, into fundamental research, and from that it can develop really into trees, into important trees that can then benefit societies. So I think that's just a perspective I came up in the last couple of years, just thinking about this development in this sense. It's very useful, and I think that's how I map it also a bit through my personal experience. Actually, I'm very happy to share with you this, and this is my last slide. So thank you for your attention.
Thank you, Alberto. Very interesting, actually, having also have seen as a viewer, by side seeing the development. Excellent. So Joe, please, over to you for the question session.
Okay. Well, thank you very much again, Alberto. That was a really interesting overview of both the light side of ADAM and also the sort of the other more interesting side as well. That was a very good overview. And now over to the students. Do we have any questions for Alberto? If so, could you raise your hand or message anything in the chat? Also waiting for the students, as I'm sure they're probably thinking of something. We'll have a comment from Manjit.
So while the students are thinking about their questions, Alberto, so a lot of people have been saying that ADAM as a type of technology makes a lot of sense for Flash. And you know that Flash, of course, is a big deal at the moment. Why is that?
Well, I think it's a very tricky question. Let's call it like this. Because, maybe I started in the beginning of the presentation from the fact of defining clearly what are the clinical needs and what are the, let's say, system requirement. And so it's true that as a pulsed machine, and when you look about Flash, you look at high dose rate, we can really see during the pulse, very high dose rate from a light machine. Now, this concept, I think it's the driving idea of the fact that Flash can be capable of doing Flash because it doesn't need degrader. So when you are also at high energy, you still preserve quite a good transmission of the beam pulse. But now from translating this to what are the real needs for Flash, that's, I think, the important question to ask, and how we map these needs, because we are just based on the idea of high dose rate. But is this all about Flash, or are there other things? And this is where maybe the question becomes more difficult to answer, in the sense of, yes, we know what light characteristics are, what could potentially be done, but is this really what the full story? This I'm not sure.
Thank you.
Okay, so we have a question in the chat from Felix. He says, thanks for the interesting talk. How do you ensure that the particles have the energy you think they have, or the energy you're intending to accelerate them to at the end of the acceleration?
So this is a question about how we ensure the particle have the correct energy during the acceleration process. And actually, I would add how we measure it, because we need to be able to know what the energy of the beam is. So we ensure it with the use of proper stabilization and feedback loop inside the RF cavities, but we measure it with this time of flight system measurement device that basically looks at the velocity, the speed of the beam outside of the linac. So that's, I think, an important, very important point from all the sides, technical, technological, and also from regulatory point of view. Yeah.
Very good, thank you. We have a question from Adam.
Yeah, it's a really confusing name to have with this project. Yeah, thanks for giving such a lucid and accessible review of this area. My question is also kind of about the energy modulation. If you modulate the energy a lot, how do you, first of all, keep synchronicity further down the linac? And also, how do you keep the focusing strength the same? Because if you're using something like permanent magnets, then your focusing strength will change with the beam energy. So I guess, yeah, how does it work, I guess, is the overview of that question.
Okay, maybe I cannot go into all the details, but just to give a glimpse, or just to give an idea, it's really goes back, maybe I can bring it back here, to how these units are made. And it's true, you are fully right. We are using permanent magnets. So how does it work? Well, to be clear, I've said we can modulate the energy within 70 and 230 MeV, but I didn't say we can go down to 30 MeV. And there is a reason for this. So the fact of using permanent magnets allow you to have quite a large energy acceptance range. It's still limited, but it's exactly what we need for this application. So the fact of having fast energy modulation really comes from the fact of using permanent magnet as well. So these, I think, are the two ingredients of this. Does it answer your question?
If I could just also add, because I think no one else has asked any questions yet. Do you do all your modulation at the start and then all the later tanks are just turned off, as it were? Or is it kind of a constant little bit along the whole length?
No, that's yes, we can switch off cavities, and that's what allow you to really have this transport through the linac. Yeah.
Just a question from myself. I think I probably already know the answer, but obviously since this is a heavy ion therapy course, would the scalability size to get a linac up for heavy ions be unrealistic for the size to be able to achieve flash with obviously heavy ions outside of a synchrotron, or is it something that could potentially be perceived?
Yeah, that's a very, very good point. And indeed, yeah, there have been studies. I also participate during my PhD to studies for design of such linac for carbon ions. But it all goes back to really what are your, let's say, clinical needs and clinical specification. And then it all goes also to, okay, what energy you want to achieve. And we know for carbon ions, the energy you require, it's maybe in the order of 400, 450 MeV per nucleon. So the linac will get longer. And that's where, for instance, you can have development in trying to increase the acceleration rate inside the cavities to keep the linac short. That's one development. And then, of course, you need to touch on the source, on the injection side. You need to have proper source to get proper ion species injected into the linac. So there are design conceptual. Now, is this acceptable also for the market in terms of size, in terms of cost? I think these are the other questions that we have technological possibility, but is this something that also from the let's say market size there is also the need or not? That's I think also the other part of the answer.
Brilliant, thank you very much. any further questions from any of the students? And if not, I will hand back to Manjit. And again, thank you very much, Alberto, for very comprehensive answers.
Thank you very
So-
much.
So, Alberto, I was thinking of one thing, and that is, we know that it takes a long time from the initial seed to the fruit to the outcome. Are there things one can do, one, to accelerate the process, or having learned the lessons through, what one could do differently if some of our colleagues, students are thinking of going in that direction?
Yeah, that's a very, very good point. And indeed, if I knew what was under the water in this iceberg picture since the beginning, yes, that's really what takes a lot of time for the thing. So I think it's not easy to foresee how from a concept you can make it a product, because you have to take into account also all the regulation, all the certification aspects, and this takes time. And so in terms of how to speed up the process is maybe know that there is something behind it already since the beginning. I think that's probably one lessons learned that maybe I can bring in this discussion. So I think it's also getting awareness of how the things work when you exactly develop from just a concept into maybe the first prototypes and so on. Yeah.
The reason I asked that question was because when we had the talk from Ed Ostron about certification, the lessons learned of being a medical device versus already starting as a medical device rather than an afterthought. So that's what I was wondering about how one can do that.
Yeah, I think it's a very important point. Yes.
Other questions from students, thoughts, comments, anybody else? If not, Alberto, thank you very much. Really appreciate you being able to join us and give us a really nice perspective of where you've come from and where Adam is now. Looking forward for the first patient treatment, by the way.
Yes. Thank you. Thank you very much.
Thank you, Alberto.
Bye-bye.
Bye-bye. Thank you. So now, Adriano, I know you've just joined us, so let's say hello.
Hello, hi to everyone. Good afternoon.
Okay, so welcome.